Okay, it looks like we are live. Great. Well, I hope you all can hear me okay. Thank you for tuning in to the Cool Science Festival. If you guys want to go ahead and share my screen, I don't know if you can hear me. Okay, thank you. Perfect. So again, thanks for tuning in, and thanks to the Cool Science Festival for having me. My name is Greg Vaughan. I'm a scientist at the USGS, that's the US Geological Survey in Flagstaff, Arizona. My background is in geology, and my primary interest is in studying and monitoring active volcanoes and geothermal areas. And although I'm based in Flagstaff, one of my projects is with the Yellowstone Volcano Observatory. And so my work is focused on studying and monitoring how much geothermal heat, that is heat that's coming from within the earth, how much heat is escaping from Yellowstone, and what does it look like at the surface, and how does it change with time? Essentially, I'm working on taking Yellowstone's temperature, which is one of its vital signs. And just like a doctor checks your vital signs when you go in for regular checkups, we monitor volcanoes by checking their vital signs, like earthquakes and ground deformation and the emission of gases and the emission of heat. And so the reason we monitor volcanoes that are not currently erupting, like Yellowstone, is the same reason you go to the doctor when you're not sick, right? You go in for regular checkups so they can measure your vital signs under normal conditions. So the purpose of regular monitoring is to establish what is normal so that we know how to recognize abnormal things if they ever happen. Changes that may be related to magma moving around underground, or volcanic or hydrothermal processes, or just seasonal cycles or human activities can cause changes at the surface. So to understand change, you have to know the background. Now, another thing that I'm really passionate about is, in addition to my research, is accurately communicating science and dispelling myths and misinformation about science in general and about Yellowstone in particular. It seems that over the last 10 or 15 or 20 years, there's been a lot of hype and misinformation and misunderstandings about Yellowstone that are sort of floating around out there. So I want to take this opportunity to play Mythbuster for a few minutes, okay? So as you all probably know, Yellowstone is often referred to in the press, and the internet, and on TV movies and docudramas as a super volcano, right? Now, there are no photographs of a super volcanic eruption anywhere, because the most recent one happened in New Zealand about 26,000 years ago. But it's not that hard to find highly exaggerated and sensationalized artist depictions of them on the internet, like the photo that I'm showing here. Now, in some of the scientific literature, the term supervolcano does have a definition. It refers to a volcanic area that has in the past had an eruption that ejected more than 1,000 cubic kilometers of stuff, ash and lava, out onto the surface. Now, that's a lot of material. These are exceptionally large eruptions and destructive. And they have occurred in geologic history. We find lots of evidence for them in the rock record. Now, supervolcanic eruptions are also referred to as large caldera-forming eruptions. So think about it like this. When you have a large underground reservoir of magma that gets emptied onto the surface, you create a void space underground that can't hold up the surface. And so the surface collapses into this void. And that's what a caldera is. It's like a big sinkhole. It's a collapse feature, not an explosion feature, as is often depicted on the internet in photographs like this one on the left. You know, it's not that the entire caldera exploded like this. It's a large collapse feature like this. And the analogy that I like to think about is this. Imagine a waterbed filled with water and covered with layers of dirt and sand and mud. Now imagine puncturing a hole, or maybe a couple of holes in the waterbed, and all the water will come shooting out those two holes. And it will excavate little small craters around those holes. But the entire waterbed is going to deflate, and all the layers of mud and sand and rocks above it are going to sink in, and it will form a big depression where the waterbed used to be. Okay, so that's how a caldera forms. It's a collapse feature, not an explosion feature. Okay, so the Yellowstone caldera, if we look at the image on the right here, we have an image of Yellowstone. The Yellowstone caldera which formed after the most recent super eruption, is really big. It's about 75 kilometers long, sort of oval shaped, and it's about 45 kilometers wide, okay? That's a really big area. And that's a pretty good reflection of how big the magma reservoir was. But it didn't look like this on the left when it was erupting, almost certainly not. Now, these caldera-forming eruptions are really big. And one of the really amazing things about Yellowstone that's not an exaggeration is that 3 out of the 5 biggest eruptions, or 5 or 6 biggest eruptions that have ever occurred on Earth that we know about in history have come from this place. Just a little over 2 million years ago, there was a really big eruption that came from this area that resulted in the formation of this large caldera we call the Island Park caldera. And I hope you can see my mouse cursor. I'm sort of outlining this caldera, the Island Park caldera. Then, about 1,285,000 years ago, there was another one, not as big, but still a really big eruption, and it resulted in the formation of what we call the Henry's Fork caldera, which is in what is now Idaho. And then, about 631,000 years ago, we had another really big, what they call super eruption, that resulted in the formation of the Yellowstone caldera, which is shown here in the purple line here. Now, many of you have probably heard or read on the internet that Yellowstone erupts at regular intervals. Sometimes they say every 600,000 years, and therefore we must be due or overdue for another super eruption. So let's talk about why that's not correct, okay? Let's do the math. So here are the numbers on this slide here. Here are the numbers. And if you calculate the time interval between eruptions, the average time interval between these super eruptions is about 714,000 years. So we're still about 80,000 years away from a point in time where we might consider saying Yellowstone's either due or overdue for another large caldera-forming eruption. But there's actually a bigger problem with this. It's really statistically, it doesn't make any sense to try to calculate or predict a recurrence based on just 2 data points. You can't do that scientifically. It's statistically meaningless. And besides, volcanoes like this don't erupt on regular, predictable schedules. So the next time you hear someone say Yellowstone's overdue, you could say, no, let's do the math and let's talk about the statistics. All right. Now, another myth that I've heard is that the caldera is so big you can see it from space. Now, I'm not sure where this comes from, because these days you can see individual cars and people from space with some of the high resolution commercial satellites that are out there. So that phrase doesn't really mean what it used to mean. But it would be meaningful if you could say something is so big we can only see it from space. That would be impressive. So let's take a look at these 2 images. The image on the left is a satellite image, a visible satellite image of Yellowstone. And the image on the right is a thermal infrared image. And really, even if you know where the caldera is and what you're looking for, you can't really make it out in these images. You can't tell where it is just from looking at it from space. And so the reason why that is because since the last really big eruption, 631,000 years ago, there have been dozens of other smaller, not so super eruptions. Lava domes and lava flows, many of which were not even that explosive. And the most recent one formed about 70,000 years ago, formed what's called, in the southwest part of the park here, there's a little lava flow called the Pitchstone Plateau Rhyolite Flow. That's the most recent one. It's about 70,000 years old. Now, these eruptions mostly filled in the caldera, so it's not a big hole in the ground anymore. You really can't see it when you look down on it from orbit. In fact, the caldera was originally discovered and mapped based on old school, boots on the ground, rock banging, geologic mapping. That's how they discovered Yellowstone's volcanic history. So Yellowstone has had a few super eruptions in the past, but smaller lava flow eruptions are far more common there. In fact, if it were to ever have a volcanic eruption again, it's much more likely to be one of these lava flows. So talking about Yellowstone as a supervolcano is really only telling part of the story. And I'm much more interested in the whole story and learning as much as we can about it. So let's talk a little bit about what Yellowstone is in reality. Well, first, it's a national park, as many of you probably know. It's actually the first national park in the world. It was established in 1872. And one of the primary reasons they made it a national park is because of the geothermal areas. There's so many thermal features there. In fact, it's the world's largest geothermal system. It contains many thousands, many more than 10,000 unique geothermal features like mud pots and steam vents, which we also call fumaroles. And of course, it has famous, very colorful hot springs, and it's very famous for its geysers. There are only about 1,000 geysers on Earth, and half of them are in Yellowstone. So it's a pretty amazing place just for some of these features. And of course, the scenery is spectacular, and there's some beautiful wildlife to see in Yellowstone. So if you ever get a chance to go, it's really one of the most amazing places. So one of the things that I work on in my research is on mapping and monitoring and trying to measure Yellowstone's thermal areas. Now, like I said, there are thousands of thermal features in Yellowstone. Mud pots, and fumaroles, and hot springs and geysers. And these features tend to be clustered together into groups, distinct areas we call thermal areas. So a thermal area is an area that has a bunch of thermal features. It has hot water mineral deposits and altered ground. And there's a lot of steam and gas coming from the ground. The ground's generally very hot, and they tend to be barren of vegetation. Vegetation, trees, bushes, grasses, are generally not really happy growing in these areas. So there are a whole bunch of distinct thermal areas, and they tend to be located along structures like faults and fractures and other natural geologic boundaries. And that's what I'm showing on this map here in red. These are where Yellowstone's thermal areas are located. Now, mapping these, and I work closely with the geologist in the national park to come up with maps of where these are. Making maps of these thermal areas is a work in progress. Partly that's because this is such a big area. We haven't found everything there is to find yet. There are still thermal areas out there that we haven't really investigated that closely yet. And it's also a work in progress because these things are always changing. Thermal areas heat up, they cool down, they develop and decay, and they move around. Change is the rule in Yellowstone, and these areas are very dynamic. Sometimes they change very subtly, and sometimes they change very obviously. And Yellowstone is such a big place that the thermal areas are so spread out and mostly inaccessible that I rely heavily on satellite and airborne remote sensing tools to help with this mapping. Now, when I say remote sensing, I'm talking about using imaging technology like specialized cameras that can act as extensions of our eyes, which allow us to see the world in a new light and in ways that we can't see with our own eyes from different perspectives. Specifically here, I'm talking about using thermal infrared remote sensing, which uses technology to make images of how much heat is coming from the ground. So the image on the right here is a Landsat 8 thermal infrared image of Yellowstone. And in this image, you can see bright areas are areas that are warmer, and dark areas are areas that are colder. This is a nighttime image acquired in the early spring, and so most of the park is covered in snow and ice, and most of the lakes are frozen. And so you can see where the cold areas are, and you can see where the thermal areas are. They're the bright areas. So I want to tell a story about one particular area in the northeast central part of the park here. So here we're looking at a thermal infrared image from April 2017, Landsat 8 thermal infrared. And you can see lakes. There are a few lakes here that I've mapped out in blue on this image, and the known thermal areas are mapped in red. You can see them outlined in red. And you can see that there are bright pixels that align with some of these areas that are outlined in red. Now, in the winter and in the spring, lakes in Yellowstone are mostly frozen, so they're cold and covered in ice, except for lakes that receive thermal input from nearby hot springs or underwater vents. And you can see here that the western extension of Tern Lake is starting to heat up and thaw. The central part of Fern Lake is starting to thaw out because you can see the bright pixels here. Now, a couple of years ago, I was sitting in my office, staring at my computer screen, looking at this image, and I noticed something odd. This patch of bright pixels here that didn't line up with any pre-existing thermal areas or any lakes. And so my first thought was, well, maybe it's a lake and we just haven't mapped it in yet. But I needed a high resolution image to look more closely. So I found in the archives a high resolution color air photo from the same area from the same year. And I discovered that this area is not a lake at all. It's a patch of ground with a bunch of dead trees and bright white altered looking soil. And it's really warm. And so I figured, okay, this is a new thermal area, or it's a thermal area that we hadn't yet included in the park database. So that's exciting. And so I started wondering, okay, well, I wonder how come it hadn't been mapped before. Maybe it hasn't always been there. So I started to look for some old archived high resolution imagery to see how this area has changed over the years. And I collected a bunch of images, and this slide here shows a whole bunch of them. So this is what it looks like now, essentially. It hasn't changed much in the last few years. And this is what it looked like in 2012, this image in the top center. And then in 2009, and then in 2006, 2003, and I found an image all the way back, a black and white air photo from 1994 that showed this area it wasn't even there. It was just healthy forest with not ponderosa, they have lodgepole pines up there. Lodgepole pines and no thermal area. So sometime between 1994 and the early 2000s, we started killing trees here, and we started creating a new thermal area started forming here. And so something started happening here. And based on looking at lots of other archived satellite images, I estimated that this new thermal area started appearing around the year 2000. And it grew very slowly. It got a little bit bigger. The trees would turn brown and die and fall over until about 2005. And then from 2005 to 2012, it grew really rapidly. It got really big really fast. And then since 2012, it hasn't been growing that much. It's slowed down, and it's been relatively stable. And so, this was a pretty exciting thing. And so the next question I asked was, what could have caused this to happen? And I did some more research, and I just want to do a quick summary of it here because I'm about to run out of time. But basically, I wondered if any earthquakes had occurred that could have caused this to happen. But this new thermal area appeared and changed without any anomalous earthquake activity going on. It does turn out that the period from 2005 to 2012, where the area grew really rapidly, the ground elevation in this region was also expanding. The ground was elevating or inflating pretty rapidly during a part of this time period. So there's probably a cause and effect relationship there. And it's also important to note that these changes are caused by changes in the flow of hydrothermal fluids underground, not caused by magma moving around. If magma were moving around, we would have heard a bunch of earthquakes. So what's happening here is the ground was inflating, opening up new fluid pathways for hot fluids to move around underground. And they found a new path to the surface, and they made it to the surface here, and the ground heated up, and gases started coming out, and it killed a bunch of trees, and this new thermal area grew pretty rapidly. So in August 2019, we did get a chance to go out and visit this area. We got to fly out there in a helicopter and get some thermal infrared images from a helicopter. You can see in the lower left here, a thermal infrared camera image shows this arc-shaped zone of the warmest ground. And the ground was pretty warm. It was, it ranged from 60 to, in some places, 80 degrees C. And just beneath the surface, the temperatures were boiling, which in this area is about 93 degrees Celsius, which is about 200 degrees Fahrenheit. So this is really hot ground here. Not a place you want to be walking around. You have to be very careful. So we went out there on the ground and carefully skirted around the edge of it to map it out and map how big it was. The area is about 8.2 acres in size, which is about the size of 4-foot soccer fields stuck together. There's no water coming from this area. There are no geysers or hot springs here. It's what we call a dry, steam-heated acid sulfate thermal area. And there's this arc-shaped zone of the warmest ground here. Another interesting observation was that where trees were laying down in contact with the warm ground, they're actually starting to carbonize, or where they were in contact with the ground, the wood was just turning to carbon, almost like they're slowly combusting. It's pretty amazing. And then there were some sulfur vents where sulfur crystals were forming on the outsides of that carbon on the tree. Another interesting observation is this little area here that's cooler. Inside this cooler zone here, in the middle of this arc, there were new trees starting to grow. So there were a bunch of dead trees, and then new, less than 5-year-old trees were starting to grow back in this area here. So perhaps this area is done growing and it's going to start coming back in the next few years. We'll see. So anyway, that's an example of some of the work that I do in Yellowstone, and some of the fun things we get to do. And well, I'll stop there and take some questions. And I just want to throw up this acknowledgement slide to show acknowledgement to all the organizations who support the work that I do in Yellowstone. And if you want to, you can go back to screen sharing, and I can take some questions. If there are any questions coming in, let me know. Thank you.